I'm Johnny Blake, I'm the research area lead for biomedical materials in the Henry Royce Institute, where we are now. Okay, so I'm going to give a very brief overview about the biomedical materials theme and enabling facilities we've got here in this building and other buildings which is part of the Royce Institute. So the Henry Royce Institute was established to develop and capitalise on the UK's world-leading excellence in advanced materials research. We're in fact a national institute with a regional footprint, so there are quite a lot of partners of the Royce. I'm not going to go through all of them, but you can see that it covers much of the map of the UK. We are now into Strathclyde as well, actually. We're based now at the Hub building, where we are today, at the University of Manchester, and several themes are being run out of Manchester, biomedical materials amongst them. So this is what is driving us to make advanced materials for a sustainable society. We've got these kind of 5 overarching themes here: health and well-being, of course relevant here today, circular economy, digital communications, and you can see there's a lot of crossover between health, well-being and digital communications, and massive opportunities for remote patient care if we can get a lot of that right, with huge challenges, of course. Sustainable manufacture and transition to zero carbon. So we're about now convening the research community. We've got fantastic facilities here in this building, so it's beyond just facilities and making materials and devices that can help for biomedical materials and devices. It's also about convening the community, bringing people together. So it's great to have you all here for in our MICRA event. We're also about promoting material science, engaging with the public, driving research and technology to solve our pressing problems. We've got 4 mission pillars. One of those is enabling national materials research foresighting, collaboration and strategy. Also providing access to the latest facilities and capabilities. We've got about £9 million worth of biomedical materials infrastructure that I'll mention as we go through this talk, and I'll make sure I'm sticking to time. Catalysing industrial collaboration and exploitation of materials research, and also fostering skills and developing our new generation of researchers as well. So more specifically, the biomedical materials theme that I am leading at the moment. Our vision is to accelerate the discovery, manufacture and translation of biomedical materials to enhance the UK's position as an international leader in the fields of biomaterials and biomedical systems and devices. So if we look at the scale of some of the problems, globally the number of individuals aged 60 plus is projected to reach well above 1 billion by 2030. I'm sure some of my colleagues here can correct me on those exact numbers. And Royce is able to accelerate discovery, manufacture and translation of some of these materials using our national resources, expertise and state-of-the-art facilities. We're supporting a new generation of biomaterials that can actually interact better with the body and stimulate and mimic the cell tissue microenvironment. And we're aiming to help accelerate provision of accessible advanced material solutions to the healthcare sector. There are some other research areas within Royce, for example 2D materials, so graphene, phosphorine. There are lots of other 2D materials that are of course becoming ever more relevant, especially for sensors. Development of flexible electronics and even neuromorphic materials. So in Royce we have a number of different themes. So bios here, we've got advanced metals processing, so making things like 3D printed metallic implants. We do a lot of that work in conjunction with the University of Sheffield, also a Royce partner. There are others, of course, worldwide working on this. Atoms to devices, chemical materials discovery. We've got materials for demanding environments. Okay, you can think about materials that are going into deep sea and corrosion, but of course the body is a demanding environment. And okay, we've got very good hip implants, but there's a lot we can still do on coatings and making these more patient-specific, for example. And again, looking at that demanding environment. Nuclear materials, they're on the 7th floor in this building right at the top, and 2-dimensional materials. We've got these technology platforms which cut across many different themes in Royce, and I'll talk to some of those that are particularly relevant for biomedical materials. So here are our current research core themes. The translation of biointeractive materials to expand the applications and innovation of existing approved materials, because we have many approved materials, but they could be repurposed or looked at for making better devices. And many of the biomaterials we use, in some cases, are not really fit for purpose. There's a lot to be done to find and develop better materials that really interact better with the body. Also, to make affordable materials for sustainable health, improving implant lifespan, digital health monitoring we were talking about earlier, the development of tissue analogues, in particular making they call them tissue on a chip, or you might have heard of organ on a chip, or human on a chip even, devices. So making cell microenvironments where we can screen drugs, we can screen cancer therapies that are patient specific. So we're doing a lot of work in that area. And of course, materials for a safer world. We've got one of our researchers embedded in Royce is developing virucidal materials. Of course, these will be really important going forwards. And antimicrobial materials and surfaces to prevent contamination. In terms of the technology platforms we've got in Royce, these were developed consulting with the communities to provide higher throughput, enhanced resolution with greater reproducibility. So we can make devices and new materials and make them much faster and test them faster. So our technology platforms are fibre technology. We can spray fibres that mimic many of the tissues in our body. This could be for wound healing, but also to try and develop some of the tissue architectures that we can screen and test drugs on, for example, with cells. Bioprinting, so this is where we can print gels with cells and build up some of the complicated architectures we see in tissues. Materials development for multidimensional printing, really that just means additive manufacture or printing materials and building them block by block. 3D dynamic stimulation and biomechanical evaluation, so we can expose some of the materials and kind of proto-tissues we're making to dynamic stimulus and exercise those tissues and also grow them in bioreactors. And bioelectronic interfacing and electronic characterization. So this is useful for things like wearables, but also when we're looking at bioelectronics, making bioelectronic measurements crossing the wet-dry divide. And we've also got extensive facilities for imaging and characterization. And many of these suites can sing together to make tissue-engineered constructs for the future, again, leveraging materials. So these are our labs upstairs. This is one of our fabrication labs where we've got this nanofibers to devices suite that's shown on the right-hand side. This is for making wound dressings and also tissue mimics. I will skip that slide. We've got bioprinting facilities, so we've got several of these extrusion machines so we can print cells with gels and cure them and then grow them in vitro environments and test them. We've got almost every imaginable kind of additive manufacturing platform that exists at the moment. You've always got this trade-off between the resolution and the build rate. So we can make things at very low resolution but at very fast speeds. But we've also got down to kind of 100 nanometer resolution for building things that are really relevant on a cell level. I'll skip over that. Then two other areas we've got a lot of work on. One is making vascular models. So we make these kind of microfluidic chips with 3D branching vascular structures, because that's one of the rate limiting steps in tissue regeneration, is getting the vasculature in there. Otherwise, your system becomes necrotic and dies quite quickly. Another area we've got a lot of research on is developing phantoms. So this is for MRI. So phantoms, that initially sounds like a strange word even to me. But for example, we've got a rudimentary brain that we've made there, and we've put MRI contrast agents, so we can see where those agents are using an MRI scanner. And what we're doing is developing these materials for the lung, for example, where that silicon can expand and contract. And if we've got the contrast agent in the right place, we can use it to train, for example, a proton beam or radiotherapy for cancer treatment in the future. Also, we've got extensive facilities on advanced medical imaging. So for doing non-destructive imaging in situ, looking at what happens over time courses, interactions between biomaterials and cells. I think the last thing that I'm going to touch on, and I'm very conscious that we've got a break and it's very important we have some coffee and some networking. I just want to talk on very briefly on this last slide about road mapping that we're doing in Royce. So one of the things that we're doing, we've done this across several of the other themes in Royce, is working with higher education institutes, industry and the public, and also clinicians actually, to roadmap and identify national materials challenges and a route to solving those. So for example, we've done a lot in materials for net zero, materials for end-to-end hydrogen, and now it's biomedical materials turn. There are lots of different things that we could roadmap, but this is what we've picked first. So we're going to be roadmapping bioelectronic materials for healthcare, and really over 3 areas: wearables, and we've had some talks today about wearables and the importance of wearables. How can we get these new materials into application faster? What are the barriers? What are the regulatory hurdles? The same for getting bioelectronics materials in vivo. There are loads of bioelectronic, electrically conductive materials. They've really come out of the semiconductors industry. They're not necessarily being designed to go inside the body. They don't break down. They don't degrade very well. We don't understand them very well. We can't get them to form to complex surfaces and give us good readouts for nursing, for example, over long periods of time, and also for in vitro models. So I think with that, I'm going to hand back to the chairs, and I thank you very much for your attention, and I look forward to interacting at the coffee break.
Thank you very much. Thank you, Jack. Any questions from floor? Yes, please.
Shout. I used to have a lot to do with the health service, and lots of people told me that it took about 16 years to get a new innovation widely accepted into the NHS. Is that still true?
Yeah, I'll also try and shout. Oh, there we go. Thank you, Alistair. I would say that that is true. It's still taking a very long time to get a new material through to clinic. There are lots of regulatory hurdles for this in particular. And however, there are some very new things that are starting to be done using artificial intelligence and machine learning. So we think that we can compress that cycle using some of these new techniques. So one thing that's particularly hot and we're looking into at Royce is something called data-centric materials, where we're trying to track all the processing that happens to those materials and the effect of those processing using artificial intelligence, for example, machine learning, to compress that development cycle. But as well, we've got the challenge of meeting the regulatory aspects, and they're changing over time rapidly, especially as these advanced therapy medicinal products, like tissue engineered products, might come closer, because they can be very disruptive, but they take a long time. So, yeah.
Yes. Okay. Just a quickly answer to that comment. Actually, that's what MICRA is trying to do. Because if we just start from engineering or material science point of view, it takes a very long time. Because if we got it like a cross-disciplinary, together with the users, the regulators, policies work together, we do the core design. That process can be accelerated. Okay, that's, I think, what's MICRA will do.
Yeah, I'm just saying, in terms of the 16 years, I mean, that was obviously fast-tracked. It's usually a lot longer than that.
Are we nearing the day when we have spray on skin for minor cuts and wounds?
Yes, I think there are already some things in that area. That for example, I know there are kind of spray on plasters now, if you call them that, but there are also some 3D printed skin type systems that people are looking at actually in the clinic nowadays. I met someone just last week at the Tissue Engineering Regenerative Medicine Society from L'Oreal, and she said she's doing work on bioprinting skin models and hair. I think I could do with some of that. But yeah.
I'm with you.
Yeah, it's because you're worth it, John.
Thank you. Thank you.
Okay, if there's no other talks, perhaps you could join me in a round of applause for all the speakers. as well, my colleagues are at the back, Emily and Mark and David, who have done all the heavy lifting in terms of the arrangements today. All these things look very simple, and it's great to have you there. So thank you on behalf of MICRA and the audience. And thank you for being our host. So we've got some tea and coffee where you have lunch, and then we'll be back at 4 o'clock for Janet's lecture.